Hi, this is Dr. Habib Ahmed, and today I'm going to demonstrate how to perform the Silvaco TCAD simulation of quantum dots solar cells. Quantum dot solar cells have been a topic of research for some time. They continue to be actively studied and developed due to their unique properties and potential advantages in the field of solar cell energy conversion. Let me tell you about a few basics of solar cell and quantum dot solar cells, and after that I will pursue with the simulation. And so here is my structure. It comprises of a transparent conductive layer, and I've assigned it as an anode, followed by a nickel oxide hole transport layer, and after that I've introduced quantum dots over here inside this structure, followed by the zinc oxide electron transport layer, and finally I have employed aluminum as a cathode layer. So let us start with the basics. What is a solar cell? A solar cell is a device that directly converts the energy of light into electrical energy through the photovoltaic effect. Then what are quantum dot solar cells? Quantum dot solar cells are a type of photovoltaic device that harnesses the unique properties of quantum dots to convert sunlight into electrical energy. Quantum dot solar cells typically consist of a layered structure like this, similar to the traditional solar cells. They include electrodes and one or more layer of quantum dots, as you can see over here, embedded within a semiconductor matrix. Then what are quantum dots? Quantum dots are nanoscale semiconductor particles with unique optical and electronic properties, and they are usually made up of materials like cadmium telluride, cadmium selenide, lead sulfide, or other semiconductor materials. For example, in this structure, I'm using cadmium telluride as a quantum dot layer. Quantum dots exhibit quantum confinement effects, which means their electronic and optical properties can be tuned by varying their size. You can also call it the bandgap engineering. Quantum dots can be engineered to have a tunable bandgap. In semiconductor quantum dots like cadmium telluride, which I've used in this structure, the bandgap energy varies inversely with the size of the quantum dot. These cyan kind of regions over here are actually cadmium telluride based quantum dots. The bandgap energy of cadmium telluride quantum dots decreases as the size of the quantum dot increases. This relationship arises because the confinement of charge carriers increases with decreasing size, leading to an increase in the energy bandgap between the valence band, or you can also call it highest occupied electron energy level, and the conduction band, or you can also call it the lowest unoccupied electron energy level. This allows quantum dot to absorb light over a broader range of wavelengths compared to the traditional solar cells, potentially increasing the efficiency of solar energy conversion. Generally, the bandgap of bulk cadmium telluride, which is a direct bandgap semiconductor, is approximately 1.44 electron volts at room temperature. And here is their energy bandgap versus the quantum dot size. So for smaller cadmium telluride quantum dots, like with their dimensions in the range of 2 to 4 nanometers, their energy bandgap is approximately in the range of 2.5 to 2.7 electron volts. Similarly, for medium cadmium telluride quantum dots with dimensions in the range of 4 to 6 nanometers, their bandgap energy varies in the range of 2.1 to 2.3 electron volts. Larger cadmium telluride quantum dots with dimensions in the range of 8 to 10 nanometers have energy band gaps in the range of 1.8 to approximately 2 electron volts. Now in this structure, basically this structure runs from 0 to 0.2 micrometers in the x direction, and from 0 to approximately 0.2 micrometers in the y direction, up to 0.195 micrometers to be exact in the y direction. And I have set the z dimension thickness to 10 nanometers. So in Silvaco TCAD, generally the built-in thickness is 1 micrometer, but we can change it. So for this case, I have set the z dimension of this structure to 10 nanometers. Now let us talk about the dimensions of the cadmium telluride quantum dots in this structure. So in y direction, it's running from 0.1 to 0.105, or you can say its height is 5 nanometers, its width is 10 nanometers, and then its thickness in z dimension is also 10 nanometers. So basically it's a 5 by 10 by 10 nanometer quantum dot. And I've introduced a few quantum dots inside this layer over here in order to simulate the quantum dot solar cell. Now the point is, what is the advantage of quantum dot solar cell? One of the key advantages of quantum dots is their ability to generate multiple excitons, electron hole pairs, from a single absorbed photon through a process which is known as multiple exciton generation. And this phenomenon can significantly improve the photocurrent and thus the efficiency of solar cells. Quantum dots have a lot of applications in research. It's an active area of research and development. They offer potential advantages such as lower manufacturing costs, improved efficiency, and the ability to be integrated into flexible and transparent substrates, expanding their potential applications beyond the traditional silicon-based solar cells. We also got some challenges in applying quantum dot solar cells. Despite their promise, quantum dot solar cells face challenges such as stability concerns due to their potential toxicity of certain quantum dot materials. Similarly, another challenge is scaling up production and maintaining efficiency over longer periods of time. In this Silvaco TCAD code, we are creating a solar cell device using zinc oxide as an electron transport layer and nickel oxide as a hole transport layer, with the cadmium telluride quantum dot light absorbing layer. Generally, metal oxide semiconductors have high mobility, greater than approximately 10 centimeters square per volt second. So a separate doping is not required. So that's why I've chosen nickel oxide and zinc oxide as hole transport layer and electron transport layer respectively. And also their band gaps are larger. For example, zinc oxide has a band gap of approximately 3.3 electron volts. Similarly, the band gap of nickel oxide is approximately 3.8 electron volts, roughly in that range. So they are transparent to visible light. They are not going to absorb a predominant portion of the visible light. I've used indium tin oxide as a transparent conductive layer because this is transparent to visible light, and it's also electrically conductive. In a solar cell, it typically forms the top electrode layer that allows sunlight to pass through it to reach the active semiconductor layers like amorphous silicon, other kind of solar cells, organic solar cells, or even quantum dots underneath. So with that preliminary description about quantum dot solar cells, let us now turn to our code. Let me open this structure figure as well. So here is the code. I have introduced meshing for in the x direction. My structure is running from 0 to 0.2 micrometers. Similarly, in y direction, it's running from 0 to 0.195 micrometers. You can see the meshing. The meshing is denser at interfaces and in the active region. Then I have introduced different regions in this structure. So first I have introduced glass as the top layer. Then I have introduced indium tin oxide running from 0 to 0.060 in the y direction. So the thickness of the indium tin oxide is 60 nanometers. After that, I have introduced nickel oxide, and its thickness is set to 40 nanometers, running from 0.06 to 0.1 micrometers. So running in the range of 60 nanometers to 100 nanometers. And basically I have optimized the layer thicknesses of all these layers. So it's not just one iteration. I've run the code multiple times and found the optical thicknesses for all these layers. This is the final simulation. Also, nickel oxide is not a built-in material inside Silvaco TCAD. So the way we introduce it, and I have posted a separate video on this as well, we introduce it using this command: user.material is equal to nickel oxide. Then we define the dimensions of the nickel oxide layer. For all these layers, I have defined the x dimensions and the y ranges, and also, as you can see over here, the z range. As I already told you that my structure runs from 0 to 10 nanometers in the z direction. Now, talking about nickel oxide, I have introduced this as a region number 3 over here using the command user.material, and later I have introduced the properties of nickel oxide. So like user.group semiconductor, I have introduced its bandgap, affinity, permittivity, density of states in the conduction band, and density of states in the valence band, electron and hole mobilities, etc. And couple of other things like SO profiles, but I'm going to discuss it later. After that, my region number 4 is gallium arsenide, running from 0.1 to 0.105 micrometers. So like running from 0.1 to 0.105 micrometers, this thin layer over here. Initially I've introduced it as a gallium arsenide layer, and then later I've introduced cadmium telluride quantum dots inside this region. I tried to use air as region number 4, but for some reason I was facing conversion problems, so I had to kind of do it this way. But there might be other solutions, like you can try other solutions to resolve that issue. But by first introducing gallium arsenide and later introducing cadmium telluride quantum dots into this region, it pretty much resolves the problem, and I'm able to run the simulation. And after that, I have introduced 5 plus 5, 10 quantum dots of cadmium telluride inside this structure, as you can see, with dimensions of 5 nanometers by 10 nanometers by 10 nanometers in the inverse z direction as well. Followed by region 15, which is zinc oxide, running from 0.145 to running from 0.105 to 0.145. So basically it's a 40 nanometers thick zinc oxide electron transport layer. And finally I have introduced aluminum from 0.145 to 0.195 as a cathode layer. Similarly, I have set the top IT indium tin oxide layer as an anode, and I have set the bottom aluminum layer as a cathode over here. Then at this point I saved the structure and I started another module of Silvaco TCAD. Here I am calling the previously created structure, and then in this section I have introduced doping for these different regions. For example, for indium tin oxide, my doping concentration is 2 into 10 to the power of 20 N-type. Similarly, nickel oxide inherently is a p-type material, so I've set the doping for nickel. Similarly, for the gallium arsenide layer over here, I've set the doping to 1 into 10 to the power of 15 per centimeter cube, and I've set the zinc oxide electron transport layer doping to 10 to the power of 15 per centimeter cube. After this, I have set some material properties. For example, for glass, the real and imaginary index, or you can also say the refractive index and the absorption coefficient for glass. And after that, I have introduced the material properties for indium tin oxide. Here you can see I have introduced a SOPRA file. In Silvaco TCAD, SOPRA files are used for defining the optical properties of materials, which is crucial for simulating solar cells. They typically include information about the refractive index and absorption coefficient as a function of wavelength. In Silvaco TCAD, these files are used to accurately model the optical behavior of materials used in solar cells. This is essential for simulating the absorption of sunlight within the semiconductor layers of the solar cell, which directly affects its efficiency. So you might see, like for example, I have introduced SOPRA file for indium tin oxide. Similarly, I have introduced a SOPRA file for nickel oxide. Its optical properties match with this material, so I've used the SOPRA file of zirconium oxide. Similarly, you can see I've introduced the SOPRA file for gallium arsenide, and similarly for cadmium telluride as well. If you go to the Atlas user manual, as you can see over here, here is the Atlas user manual. You can search for SOPRA, and here you can go to the SOPRA database. You can see SOPRA files for so many different materials. Then you can search for like SOPRA file for gallium arsenide, and here you see the SOPRA file containing the optical properties information for gallium arsenide. N over here represents the refractive index and K represents the absorption coefficient. So that's how you introduce the optical properties of materials into Silvaco TCAD. Now, Silvaco TCAD contains the optical properties information for a lot of materials, but not for all materials. For example, one of the layers of our structure is zinc oxide, and here is a color chart. So you see this electron transport layer, which is based on zinc oxide. Silvaco TCAD does not have the optical properties, or it does not have the SOPRA file for zinc oxide. So what do we do? What do we do in that case? In that scenario, when we don't have a built-in SOPRA file for a particular material, we have to create one, and we have to call that file into our Silvaco TCAD program. And how do we call it? We call it using index.file is equal to zinc oxide.nk. I've named this file as zinc oxide.nk. Let me go to that particular file. Here is the zinc oxide file, and if you go to the type of this file, it's designated as nk file. So we open that file. Now we basically got 5 entries over here, or you can say 5 ordered triplets. The first column represents the wavelength. The second column represents the refractive index, and the third column represents the absorption coefficient. So basically the refractive indices and absorption coefficients are a function of wavelengths. So we create that file and then we call that file into our Silvaco TCAD code. Then following the sequence of my code, I have introduced different models for simulating this structure. Then I'm using Newton method for the numerical calculations of this semiconductor device. There are several different numerical methods that can be used for calculating the solutions to semiconductor device problems. Basically 3 types: Gummel, Newton, and Bloch. Here I'm using Newton. Then I want to look at different output parameters, the band diagrams, current flow lines, permittivity, etc. I've set the anode work function. The anode is basically indium tin oxide, and its work function is around 5. So I've set the work function of indium tin oxide to 5, and I've set the work function of aluminum to 4.28. Generally, the work function of aluminum is around 4.3 electron volts. Then I save the structure and I plot the structure. At this point, I want to look at the IV characteristics of the solar cell initially under dark conditions. So I've created a block of code for looking at the IV characteristics of the solar cell under dark conditions. I'm sweeping the anode voltage from 0 to 1.5 volts at a step of 0.05 volts. And after that, I want to look at the IV characteristics of the solar cell under light conditions. So the solar spectrum typically extends from the infrared region to the ultraviolet region with the wavelength range from 0.2 to 3 micrometers. But the intensity is not uniform. The path length of the light in the atmosphere depends on the angle, which will vary with the time of the day. And this is given by air mass number, which is secant of the angle between the sun and the zenith, or the vertical direction. Now, air mass 0 represents the solar spectrum outside the Earth's atmosphere. Similarly, AM1, which is the angle, is when the angle is 0. Then in that scenario, so when the angle is 0, we call it AM1. Similarly, when the angle is 60 degrees, we call it air mass 2. When the angle is 48.2 degrees, we call it AM 1.5, or we can call it air mass 1.5. Now, what is the significance of air mass 1.5? And I basically introduced it over here. I've defined a beam, and I am introducing air mass 1.5 beam. So basically, there are certain standard test conditions which refer to the set of environmental and operational parameters under which the performance of a solar cell is measured and rated. And the key parameters are light intensity, or we can also call it irradiance. Secondly, the spectrum, and thirdly, the temperature. Talking about irradiance, the intensity of sunlight falling on the solar cell surface. So the standard test conditions specify that the light intensity should be 1000 watts per meter square, or we can say 100 milliwatts per centimeter square. And this is roughly equivalent to full sunlight at noon on a clear day. Talking about the spectrum, the spectral distribution of sunlight, which at standard test conditions is based on the air mass 1.5 spectrum, this kind of standardizes the wavelength distribution of sunlight used in testing. So it's basically a standard that our angle to the zenith should be 48.2 degrees, resulting in air mass 1.5. Similarly, the temperature of the solar cell during testing should be 25 degrees Celsius, or you can say 77 degrees Fahrenheit. These conditions allow manufacturers and consumers to make direct comparisons between different solar panels, ensuring that performance metrics like efficiency and power output are measured under consistent and reproducible conditions. So at this point, we are actually interested in solar cell analysis under light illumination, and we can turn on the illumination by assigning beam intensity on a solve statement, as you can see over here. As we had assigned AM 1.5 on the beam statement, this corresponds to the standard test conditions. Like we can see over here, we have assigned it as AM 1.5 corresponding to the standard test conditions. However, in some cases we may encounter convergence difficulties, and we may need to ramp up the light intensity as shown over here. Now, I have personally simulated a lot of different kinds of solar cells, but this is a critical part. We face convergence difficulties, so it's always a good thing to ramp up this intensity to you can say 1 kilowatt per meter square. This is one sun. So this then becomes 100 watt per meter square. This becomes 10 watt per meter square, and this becomes 1 watt per meter square. Now the next step is to extract the illuminated forward current voltage characteristics. And for that purpose, the first thing we do is we define an output file for capturing the data. So we create a log file with this name solar_light.log, and then we sweep the anode voltage from 0 to 1.5 volts at a step of 0.05. So this specifies that all current voltage characteristics extracted from any solve statement will be captured into this solar_light.log file. And here we have chosen a shorter voltage step to improve the accuracy in obtaining the open circuit voltage. Essentially, we will resolve the open circuit voltage when accuracy comparable to the final voltage step size. After that, we plot the IV characteristics of the solar cell under dark and light conditions into the same figure using the overlay command, and we save the structure at this point under light conditions, and we plot the structure to look at like photon absorption rate and photo generation rate, etc. After that, we call this file using this command, and we use certain formulas to calculate the short circuit current density, open circuit voltage, power, the maximum power, maximum voltage, maximum current, the fill factor, and the efficiency. Followed by another module of Silvaco TCAD, and in this module we actually want to look at the solar spectrum and the internal and external quantum efficiencies. So we define the parameters of the different materials inside the structure once again, and then we ramp the wavelength in the range of 0.04 to 1 micrometers, and finally we use certain formulas to calculate the internal and external quantum efficiencies, and then we plot them into the same figure, and finally we quit the program. So now let me run the program. Here is the structure. If I go back to the program, At this point, the program is running the IV characteristics of the solar cell under dark conditions. It's ramping up. Okay, so here is the structure. We can look at different things for this structure. For example, we can right click on the structure, then click display, and if we click on this icon, it shows us the meshing. And as you can see inside this structure, that the meshing is denser at the interfaces and also around the active layer. However, it is sparser in the regions away from the interfaces and away from the active layer. Now we go to display and uncheck on this icon and hit apply once again. We can click on this icon to look at the electrodes for the structure. So we can see that our indium tin oxide layer is our anode, and similarly the aluminum layer at the bottom is our cathode. Let me check the code once again. So right now it's ramping up the light intensity, and it's going to take around 10 minutes performing that. So we got plenty of time to spend on this figure while our code is still simulating. So what else can we look at? Apart from the meshing, we can also look at the doping profile. So if we right click on the structure and we click on this icon, which is contours, then we click on define contours. Instead of absolute net doping, you might like to click on net doping to figure out the level of doping and also the type of doping in different regions. For example, my doping is around 10 to the power of 19. N-type, as you can see over here from the color chart, 10 to the power of 19 per centimeter cube for the zinc oxide electron transport layer. Similarly, for the nickel oxide layer, my doping is around 10 to the power of 19 per centimeter cube, and this is, as you can see from here, the doping for nickel, which is our whole transport layer, is p-type. Apart from the dopings, we can also look at the energy band diagram of the structure under thermal equilibrium. So we uncheck on contours once again. Okay. And let's also keep an eye on the simulation. So it's going to take 6 more minutes to ramp up the light intensity from 1 watt per meter square to 1000 watts per meter square. We can also look at the energy band diagram of this entire structure. So for that purpose, we go to tools, we click on cut line, and we draw a cut line across the ITO layer, then the nickel oxide layer, then the cadmium telluride quantum dot, followed by a zinc oxide layer, and then the bottom contact, which is our cathode. So here is the net doping. We are more interested in looking at the energy band diagram of this structure. So we click on EC of T, EV of T, electron quasi-Fermi level, and similarly whole quasi-Fermi level, and uncheck net doping. So here is our energy band diagram for this entire structure under thermal equilibrium. This side over here corresponds to the zinc oxide layer. As we can see there, this is a wide band gap material. Similarly, the right side over here corresponds to the nickel oxide layer. In the middle, we have the cadmium telluride quantum dot, I'm also interested in looking at the energy band gaps. So we right click on this figure, we go to display, uncheck EC of T, electron quasi-Fermi level, EV of T, and hold quasi-Fermi level, and click on the energy band gap. So as you can see, here is the energy band gap. Now the band gap of nickel oxide is approximately 3.4 electron volts. Similarly, the band gap of zinc oxide is approximately 3.3 electron volts. Talking about the cadmium telluride quantum dot, its band gap is approximately 1.49 electron volts. Now, how do we compare the band gap of the cadmium telluride with the band gap of the gallium arsenide layer? Before answering that question, let us peek into our code. So we still got approximately 4 minutes prior to the simulation getting to the IV characteristics under light conditions. So in order to perform a comparison of the band gap of cadmium telluride and gallium arsenide inside this quantum dot matrix layer, what we can do is, let me delete this figure over here. We go to tools, we go to cut line, and we can draw a horizontal cut line over here. This is not horizontal. First we need to click on horizontal. So we draw a horizontal cut line starting from the gallium arsenide layer. So now this figure shows the plot for net doping. So we right click on this figure, we go to display, and then we click on the energy band gap, and let us uncheck the net doping. So now here is the energy band gap profile across the active layer, starting from the gallium arsenide. For gallium arsenide, the band gap is approximately 1.42 electron volts, and then for cadmium telluride, the band gap is approximately 1.49 electron volts. We still got approximately 2 minutes, so let us wait until then. The light intensity is still ramping up. Okay, Now it's sweeping the voltage from 0 to 1.5 volts under light conditions at 1000 watts per meter square, or you can say 100 milliwatts per centimeter square. It's still ramping up at 0.5 volts, 0.55 and so on. Here is the IV characteristics of the solar cell under dark and light conditions. This is the power curve. So here we see that our open circuit voltage is approximately 1.1 electron volts. If you want to figure out for certain, we can go to the variables command, and from here we see that our open circuit voltage is approximately 1.05 volts. Similarly, the short circuit current density is approximately 32.5 milliamps per centimeter square. The maximum voltage is 0.85. The fill factor is 76.67. The efficiency of this solar cell is 26.13% approximately, which is a really good efficiency. This red curve represents the IV characteristics of the solar cell under dark conditions, and the green curve represents the current voltage characteristics of the solar cell under light conditions. Similarly, here is the power curve, which is the product of the current and voltage. And as you can see that we see the maximum power at this point over here. If we go back to the variable tab once again, we see that the maximum power is achieved at maximum voltage of around 0.85 volts. So looking at this curve, it's around at the maximum point is around at 0.85 volts. Here is the spectral response range of the solar cell, and the spectral range of this solar cell is approximately in the range of 0.15 to, you can say, 0.55 micrometers. Similarly, we can see the internal and external quantum efficiency of the solar cell from here. Okay, something went wrong. Cool, we got it. So here is a comparison of the internal and external quantum efficiency of the quantum dots solar cell. The external quantum efficiency for this solar cell is approximately 25% at approximately 320 nanometers light wavelength. So this is how we simulate the quantum dot solar cells. Obviously, there can be like more number of ways to simulate the quantum dot solar cells. I gave it a try, and hopefully this is a useful simulation for people working on quantum dot solar cells. Here is the quantum dot solar cell structure under light conditions, and this is a useful figure. So if we right click on the structure, we go to display, We click on contours, go to define, and then click on we can click on photon absorption rate or photo generation rate. So if we click on photon absorption rate, it gives us the photon absorption profile across the structure, and here is the color chart. So as you can see that the photon absorption is dominating in the quantum dot matrix region, and even inside this layer the cadmium telluride quantum dots absorb more light, represented by kind of the orange reddish color, as compared to the greenish region which corresponds to the gallium arsenide. If you want to figure it out for certain, what we can do is we can go to tools, cut line. We can draw a vertical cut line across the cadmium telluride quantum dots layer, and here is the photon absorption rate across the structure. As we can see that the photon absorption is pretty dominant in the cadmium telluride layer as compared to the other layers inside the structure. Similarly, if you want to perform a comparison of the photon absorption inside the cadmium telluride versus the gallium arsenide layer, we can draw a horizontal cut line across this structure, and here is a comparison of the photon absorption rate of the cadmium telluride quantum dots versus the gallium arsenide regions. Similarly, we can also look at the photo generation rates inside this structure under light conditions, as you can see from this figure. So here is a comparison of the photo generation rate. We go to display, define, contours, we go to linear. Let me see how it looks now. It gives a better look of the structure as compared to the log one. So this is how we perform the simulation of quantum dots solar cells. I hope this simulation was useful for you. Until next time, take care. Adios.